Everything in the universe spins. The planet beneath your feet, the star it orbits, the galaxy that star calls home. From the smallest dust grain caught in the friction of a collapsing cloud to the largest cosmic structure we have ever mapped. Rotation is not a feature of the universe. It is a fundamental condition of it, which is why what JWST found, 12 billion light-years away, at the edge of everything we can see, should not exist. It is a galaxy more massive than anything our own cosmic neighbourhood has ever produced. It has already lived a full life, built hundreds of billions of stars, and then inexplicably stopped. And it has never spun, not once, not even slightly. In a universe where everything rotates, this galaxy simply does not, which raises three questions that have been haunting astronomers since the data came back. How does a galaxy this big form this fast? How does it stop making stars when the universe is barely 2 billion years old? And how, in a cosmos governed by angular momentum, does something this enormous simply never begin to turn? Before we can understand why this galaxy is so profoundly strange, we need to understand the rule it broke. Rotation is not incidental to the cosmos. It is written into the physics of the universe from its earliest moments. When the Big Bang launched matter outward in a vast seething flood of hydrogen and helium, that matter was not perfectly uniform. There were subtle overdensities, regions where gravity pulled marginally harder than their surroundings. As gas began to fall toward these gravitational wells, it did not fall in cleanly. It fell from all directions simultaneously, and because those directions were never perfectly symmetric, the infalling material carried angular momentum. It arrived spinning, and because angular momentum is one of the most rigorously conserved quantities in all of physics, meaning it cannot simply vanish, it can only be transferred, the resulting structures had no choice but to rotate. This is why every disk in the universe is a disk. The swirling arm of the Milky Way, 100,000 light-years across, the rings of Saturn, the flat protoplanetary disk from which the Earth itself condensed. All of these structures are what happens when collapsing rotating gas can no longer fall inward and instead flattens into a plane, spinning around a common centre. The mathematics of this process, first worked out rigorously in the 1960s and refined through decades of simulation, predicts that angular momentum is imprinted on every structure from the moment it begins to form. You cannot build a galaxy without spinning it. The physics simply does not permit it, and the evidence bears this out completely. Of all the galaxies astronomers have ever measured, thousands of them across billions of years of cosmic time, the overwhelming majority rotate. Some rotate gently, their outer arms barely moving relative to their cores. Others are disk galaxies wound so tight that their stars complete a full orbit in less time than it has taken multicellular life to evolve on Earth. The Milky Way itself rotates at approximately 220 kilometers per second at our position within it, a figure so well established that it underlies every mass estimate we have ever made for our own galaxy. Rotation is not a property of some galaxies. Rotation is a property of galaxies. So when a team of astronomers pointed the James Webb Space Telescope at a region of sky catalogued in the XMM SURVS field, a deep survey patch studied for years with ground-based instruments, and received spectral data suggesting that a galaxy weighing 330 billion solar masses had essentially no ordered rotation at all, first instinct was not wonder, it was suspicion. Something had to be wrong with the data, but while the suspicion was understandable, it was what the data refused to do, refused to yield any gradient, any systematic velocity shift, any signature of a spinning disk that would prove to be the beginning of something far larger. The galaxy has a designation that sounds like a filing code, XMM VIDI1 2075. It sits at a redshift of Z 3.449, which is the universe's way of telling us how far the light has been stretched on its journey to us. Translated into human terms, this means we are looking at light that left this galaxy when the universe was approximately 1.8 billion years old. To put that into context, the universe today is 13.8 billion years old. When this galaxy's light began its journey toward us, the universe had not yet reached the age that our own solar system has today. We are looking at the very childhood of the cosmos. And in that childhood, this galaxy had already done something that should have taken 10 times as long. Previous observations with the W.M. Keck Observatory in Hawaii, conducted as part of a survey called MAGAS-3NE, standing for Massive Ancient Galaxies at Z greater than 3 near infrared, had confirmed XMM Vid1 2075 as one of the most massive known galaxies from this era. Its stellar mass clocks in at 3 times 10 to the 11th solar masses, in plain language 330 billion times the mass of our Sun. The Milky Way, for comparison, contains somewhere between 200 and 400 billion solar masses across its entire structure. This galaxy, at less than 2 billion years old, had already assembled a stellar population rivaling or exceeding our own galaxy's total. That alone is a problem. The standard model of galaxy formation, the framework called lambda CDM, which describes a universe dominated by dark energy and cold dark matter, predicts that galaxies should build up gradually, accreting gas from their surrounding dark matter halos over timescales of billions of years. Astronomers refer to this as the downsizing problem. The most massive galaxies in the early universe appear to have formed their stars too quickly, too efficiently, and too soon for the standard model's timescales to accommodate them. XMM Vid1 2075 is an extreme case of this problem. By the time it was 1.8 billion years old, it had already assembled more stellar mass than most galaxies will ever contain. But here is the second layer of strangeness. Not only had this galaxy built an enormous stellar population in record time, it had also completely stopped. Its star formation rate at the time of observation was measured at less than 1 solar mass per year, which is the galactic equivalent of silence. Our own Milky Way produces approximately 1 to 3 solar masses of new stars per year. A galaxy in the full vigour of star formation might produce thousands. XMM Vid1 2075, despite its enormous bulk, had essentially gone dark. Astronomers call this a quiescent galaxy, a euphemism for something that has, by all measurable indicators, finished living. This double strangeness, forms too fast, dies too young, already places XMM Vid1 2075 in a rarefied and troublesome category. Massive quiescent galaxies in the early universe are among the most challenging objects for any theory of galaxy formation to explain. They require not only that star formation accelerate to extraordinary rates in the first few 100 million years of cosmic history, but also that something powerful enough to shut the whole process down arrives and acts on precisely the right timescale, hundreds of millions of years before the galaxy is even observed. The mechanism behind this shutdown, this galactic quenching, is itself one of the most debated topics in modern astrophysics, with active galactic nucleus feedback, supernova-driven winds, and gas exhaustion all competing for primacy. But neither the stellar mass problem nor the quenching problem is the deepest mystery here. Both of those were known, at least in general terms, before JWST turned its instruments toward this field. What was not known, what no one had seen before, in any galaxy at this distance from us, was what the new data showed when astronomers asked the most basic kinematic question you can ask about a galaxy: is it spinning? The answer that came back rewrote the question. To understand what JWST measured and why it was so unexpected, you need to understand how astronomers determine whether something is rotating when it is 12 billion light-years away. The technique relies on the Doppler effect, applied to starlight. When a galaxy is rotating, one side of it is moving toward us and the other side is moving away. The light from the approaching side is compressed slightly, shifting toward the blue end of the spectrum. The light from the receding side is stretched, shifting toward the red. If you can resolve a galaxy well enough to separate the spectra from its different spatial regions, you can map this velocity gradient across its face. A rotating galaxy reveals itself as a systematic pattern, blue on one side, red on the other, with the velocity magnitude building from the center outward. This technique has been used to measure galactic rotation for over a century, and it is so well established that it now serves as a primary tool for estimating galactic mass. The problem with applying it to distant galaxies is resolution. a galaxy at redshift 3.4 appears extraordinarily small in the sky. The entire half-light radius of XMM-VED 1275, the radius within which half its total light is contained, spans just 2 kiloparsecs, or roughly 6,500 light-years. At its distance from us, this subtends an angle of approximately 0.24 arcseconds on the sky. Ground-based telescopes, even equipped with adaptive optics systems that partially compensate for atmospheric blurring, struggle to resolve structures on this scale in the infrared wavelengths needed to study galaxies at this redshift. This is where JWST's NIRSpec IFU, the Near-Infrared Spectrograph's integral field unit, represents a genuine revolution. The IFU is not a camera and not a single spectrograph. It is both simultaneously, applied to every point in a 3x3 arcsecond patch of sky. It divides that patch into spaxels, spatial pixels, each 0.1 arcseconds on a side. At the distance of XMM-VED 1275, each of those spaxels corresponds to approximately 730 parsecs, or about 2,400 light-years. For the first time in history, astronomers could obtain a full kinematic map of a galaxy this distant. Not a single spectrum averaged over the whole object, but resolved velocity measurements across dozens of individual spatial regions within it. The observations were taken on August 2nd, 2024, as part of JWST Cycle 2 program GO29WA3, led by Ben Forrest of the University of California, Davis. The galaxy was observed for 9 hours using the G235 MF170LP grating and filter combination, which covers wavelengths from 1.66 to 17 micrometers, the spectral range needed to capture the key absorption features from XMM-VED-1-275's stellar population as they appear at its redshift. The central spaxels achieved a signal-to-noise ratio of approximately 40 per wavelength element, which is more than sufficient for kinematic analysis. The team processed the data with scrupulous care. They applied Voronoi binning, a technique that groups adjacent low-signal spaxels together until each combined region reaches a minimum signal-to-noise threshold. To ensure that every velocity measurement was statistically reliable, they used a sophisticated spectral fitting code called PPXF, penalized pixel fitting, to extract the stellar velocity offset and stellar velocity dispersion from each spatial bin by comparing the observed spectra against template libraries of stellar populations. They accounted for the distorting effects of the instrument's point spread function. They ran Monte Carlo iterations to quantify uncertainties. The methodology was not casual, and then they looked at the velocity map. In a rotating galaxy, the velocity offset plot, which shows how much faster or slower each region is moving relative to the galaxy's systemic velocity, looks like a smooth dipole, blue values on one side, red values on the other, with the magnitude of the shift reflecting the rotation speed. It is one of the most recognizable patterns in observational astronomy. In XMM-VID-1 2075, that pattern was absent. Every spatial bin across the galaxy showed a velocity offset of less than 100 km per second relative to the systemic velocity. The median absolute deviation across all bins was just 26 km per second. There was no gradient, no dipole, no systematic pattern of any kind that would indicate ordered rotation. To quantify this result rigorously, the team calculated a quantity called the spin parameter, denoted by the Greek letter lambda, with a subscript indicating measurement within the half-light radius. The spin parameter is a dimensionless number that captures the balance between rotational velocity and velocity dispersion in a galaxy. Essentially, how much of a galaxy's internal motion is organized rotation versus chaotic, random movement. For a fast-rotating disk galaxy, lambda would approach values of 0.5 to 0.8. For the most massive, kinematically settled elliptical galaxies in the nearby universe, the giant dead ellipticals sitting at the centers of clusters, which are themselves classified as slow rotators, lambda values typically fall below 0. 2 for XMM-VD1 2075, the measured spin parameter was 0.101, plus or minus 0.018. This is the stillness problem. A galaxy 330 billion solar masses in weight, existing when the universe was younger than 2 billion years old, with a spin parameter indistinguishable from the most kinematically evolved elliptical galaxies in the present-day universe. Everything the physics of galaxy formation predicted should produce a rapidly rotating system had instead produced something that barely moved at all, and what the spin parameter alone could not explain, what made this finding genuinely extraordinary rather than merely anomalous, was the timeline, because those slow-rotating local ellipticals achieved their kinematic state through billions of years of mergers, interactions, and gradual angular momentum loss. XMM-Vid1 2075 had arrived at the same state with less than 2 billion years of cosmic time in which to do it. The two other galaxies in the same JWST program, XMM-Vid3 1120 and XMM-Vid3 2457, both similarly massive quiescent galaxies at essentially the same redshift of Z349, showed no such anomaly. Both exhibited substantial rotation. One of them, XMM-VD3 2457, showed rotational velocities reaching approximately 400 km per second. They behaved exactly as theory predicted. XMM-VID1 2075 did not. Before the team could begin to ask what had happened to this galaxy's rotation, they had to first eliminate the most straightforward alternative explanation. Was it possible that XMM-VID1 2075 was actually a fast rotator that simply observed face-on, so that its rotational motion was directed away from us rather than across our line of sight, making it invisible to the Doppler technique? This is a genuine pitfall in kinematic studies, and the team addressed it directly. The observed axis ratio of the galaxy, the ratio of its short axis to its long axis as seen on the sky, gave an inclination angle of approximately 28 degrees from face-on. At that inclination, the line-of-sight component of any significant rotation would be easily detectable in their dataset. They also checked for the expected kinematic signatures of a rotating disk viewed at this angle, including higher-order moments of the velocity distribution. None of them appeared. The team was confident XMM-VID1 2075 was not a face-on fast rotator. It was a genuine slow rotator, the first ever confirmed at redshift greater than 2. The first in the history of extragalactic astronomy found this young, this massive, and this still. While that measurement alone should have closed the chapter, it was what lay off to the side of the galaxy, a smear of excess light, barely visible against the cosmic background, that opened the next one. The universe does not generally destroy angular momentum. Physics is quite strict about this. Angular momentum is conserved, which means if a system loses its spin, that spin must go somewhere. It must be transferred to something else, absorbed into chaotic thermal motion, or cancelled out by an opposing contribution from another system. There is no mechanism by which a rotating galaxy simply stops, any more than a spinning figure skater can slow down without friction or extending their arms to transfer momentum outward. So the question the JWST data immediately raised was not just, where did this galaxy's rotation go, but the more physically precise question, what mechanism could possibly remove angular momentum from a system this large, this early in cosmic time? In the present-day universe, we know of one reliable process that can do it. Two galaxies collide. When galaxies merge, the outcome for angular momentum depends critically on the geometry of the collision. If two disk galaxies approach each other with their rotation axes roughly aligned, both spinning in the same sense, like two clockwork gears turning the same direction, the merger tends to preserve or amplify the total rotation of the combined system. Major mergers of this type can produce fast-rotating elliptical galaxies or reignite star formation in spectacular starbursts. But if two galaxies approach with opposite rotational senses, one spinning clockwise, the other anti-clockwise, the story is completely different. When they collide, their angular momenta partially cancel. If the geometries are right, the cancellation can be nearly total. The resulting merger remnant inherits the combined stellar mass of both progenitors, but a fraction of their original rotation. The stars, no longer constrained by a coherent disk structure, settle into chaotic, dispersion-dominated orbits that move in every direction at once, without any net rotation. System becomes what astronomers call dispersion-supported, held up against gravity not by rotation, but by the random kinetic energy of its stars. This is the formation pathway that produces slow-rotating elliptical galaxies. It is how we believe the giant dead ellipticals sitting at the centres of galaxy clusters came to be. It is supported by decades of N-body simulations, and by the systematic observation that slow rotators in the local universe almost invariably show signatures of major merging in their stellar populations, their morphologies, and their kinematics. The question is whether this process can plausibly operate on the timescale available to XMM-VD1 2075. And here the JWST data offers a tantalizing piece of physical evidence. When the team collapsed the IFU data cube along its spectral axis to produce a deep image of the galaxy, they saw something in the northeast quadrant of the frame, a region of excess light extending away from the main body of the galaxy at low surface brightness. In the NRCam imaging from the separate deep dive program, which had observed XMM-VD1 2075 in 4 bandpasses, the Cersic modelling residuals showed the same feature clearly. After subtracting the best fit smooth galaxy profile, a blue excess remained in the northeast, consistent with the presence of a secondary structure, possibly a companion galaxy in the process of interacting with the system. This is not proof of a counter-rotating major merger. The light ratio between this feature and the main galaxy body is greater than 10:1, suggesting the companion is substantially less massive than XMM-VD1 2075 itself. A minor merger between a large galaxy and a much smaller one typically transfers stars to the outskirts of the larger galaxy and can incrementally reduce its spin over multiple encounters, but the efficiency of angular momentum removal through minor merging alone is generally considered insufficient to produce the observed level of kinematic suppression on such short timescales. Multiple minor mergers accumulating over billions of years can do it. 1 or 2 in less than 2 billion years probably cannot. Yet the major merger scenario, a single catastrophic collision between 2 massive, counter-rotating galaxies, has its own difficulties. The timing is savage. For XMM-VD1 2075 to reach its observed state by a redshift of 345, the major merger would have had to occur, the subsequent starburst would have had to rage and exhaust the galaxy's gas supply. The quenching mechanism would have had to activate and suppress further star formation, and the kinematic transformation from fast to slow rotator would have had to complete, all within perhaps the first 1.3 billion years of cosmic time. Simulations of galaxy mergers suggest that the kinematic relaxation of a merger remnant typically requires several 100 million years after the actual collision. Stack on the timescale for the starburst, the quenching, and the cosmological time needed for 2 massive galaxies to form and approach each other in the first place, and the timeline becomes extraordinarily compressed. It is not impossible, but it is tight enough to make cosmologists uncomfortable. This is the timing paradox. The merger hypothesis explains the kinematic state but strains the available time, and it is not the only explanation on the table. A second hypothesis, suggested by the Magneticum cosmological simulation suite, offers a different formation channel entirely. In simulations of the early universe, there are rare cases where a massive galaxy can have its angular momentum suppressed, not through a merger, but through an isotropic infall of gas, material falling in from all directions simultaneously, without a preferred axis. When gas falls in isotropically, the angular momentum contributions from different directions partially cancel each other, and the resulting galaxy never acquires substantial net rotation in the first place. In the Magneticum simulations at a redshift of approximately 3.4, all identified slow-rotating quiescent galaxies were formed through this channel, and the kinematic transformation occurred before or during the starburst phase that subsequently triggered AGN feedback and star formation quenching. In this scenario, XMM-VD1 2075 did not lose its rotation through a cataclysm, it was born without it. The excess light feature to the northeast might then represent the first of many future minor mergers, dry, gas-poor collisions that that will gradually build up the galaxy's outer envelope over the next several billion years, eventually turning it into something that resembles the giant slow-rotating ellipticals we see in nearby galaxy clusters today. This is, to my mind, one of the most philosophically striking possibilities the data raises. The idea that this galaxy never had a normal childhood, that it was dispersion-dominated from birth, shaped by an asymmetric gas collapse rather than a violent collision, implies that the path to kinematic maturity is not a single road. The universe, it turns out, has more than one way to build something that does not spin. A third possibility refuses to be ruled out entirely. The apparent companion feature and the kinematic state of XMM-VD1-2075 might be unrelated. An observational coincidence in which a low-mass interloper happens to sit near the projected position of the larger galaxy, while the latter's stillness arose through an entirely different mechanism. Distinguishing between these three pathways, catastrophic counter-rotating merger, isotropic gas infall, or multiple minor mergers, requires kinematic data of substantially greater depth and resolution than currently available. The skewness and kurtosis of the velocity distribution within each spatial bin, the third and fourth statistical moments, which encode information about asymmetric and non-Gaussian motions, could in principle discriminate between merger scenarios, but the current data's signal-to-noise ratio in the outer bins is insufficient for a reliable characterization of these higher-order moments. The galaxy has given up its most dramatic secret. It has not yet given up its origin story. There is a particular quality of silence that descends on a research group when data refuses to cooperate with expectation. It is not the silence of failure. It is more textured than that, edged with something that takes days to identify as the beginning of excitement. Ben Forrest, a research scientist in the Department of Physics and Astronomy at the University of California, Davis, knows that silence well. He has been chasing massive ancient galaxies for the better part of a decade. Forrest came to these objects through the Magaz-3 survey, which he has been part of since its early years. The survey's logic was straightforward, if audacious. Identify the most massive galaxies in the early universe using deep near-infrared photometry from the Vista Deep Extragalactic Observations Survey, the Video Survey, which mapped hundreds of square arc-minutes of sky in the near-infrared from the Paranal Observatory in Chile, and then confirm their redshift and stellar properties with spectroscopic follow-up at the Keck Observatory. This is not a trivial program. Spectroscopic confirmation of galaxies at redshift 3 to 4 requires hours of telescope time per object, and the number of objects bright enough and well enough positioned to be observable from Mauna Kea is limited. Magaz-3 built its confirmed sample with painstaking efficiency object by object. XMM-VD1-2075 appeared in the survey's candidate list because of its near-infrared brightness, a K-band magnitude of 20.8A, and its red spectral energy distribution, which suggested a high photometric redshift, and Keck spectroscopy confirmed the redshift at Z 3.449 and measured a stellar mass of 330 billion solar masses, with a star formation rate below 1 solar mass per year. The galaxy became one of the survey's priority targets. It was, in the language of the field, a compelling case, massive, quiescent and early, but compelling cases required more than Keck could provide. To understand the internal dynamics of a galaxy this compact at this redshift, to ask not just what it weighed and whether it was dead, but how it moved, required the resolving power and sensitivity of something that did not exist when Forrest first identified the galaxy as a target of interest. It required JWST. The proposal was submitted. The program was assigned the designation GO 2913. The observations were scheduled for August 2nd, 2024, targeting 3 of the most massive spectroscopically confirmed quenched galaxies in the survey, XMM-VIDE1-2075 and XMM-VD3-12457, all 3 sitting near Z 3.5, all 3 qualifying as ultramassive by any reasonable definition. The scientific goal of the program was to obtain spatially resolved stellar kinematics for massive quiescent galaxies at this epoch. to ask, for the first time with sufficient precision, whether galaxies this massive and this old had structured internal motion, and what that motion could tell us about how they formed. When the JWST data came down and the initial reduction was complete, the first thing the team would have inspected was the velocity map, the spatial plot of stellar velocity offsets across the face of each galaxy. For XMM VI D3 2T457, the map showed something expected and reassuring, a clear velocity gradient, with one side of the galaxy moving at up to 400 km per second faster than the systemic velocity, and the other side correspondingly slower, a disk in rotation, just as theory predicted. For XMM Vid 31120, the picture was more complex, but still showed regions of elevated rotational velocity. Also as expected, then there was the third map, the one for XMM Vid 1 2075, no gradient, no dipole, every bin sitting within less than 100 km per second of the systemic velocity, with a median absolute deviation of 26 km per second across the whole system. At the centre of the galaxy, the stellar velocity dispersion was running at approximately 500 km per second. The stars were not still, they were moving at extraordinary speeds, but those speeds were random, chaotic, pointing in every direction at once like a compressed storm rather than the coherent current of a spinning disk. The galaxy was not cold and quiet. It was violently agitated. It was simply agitated in a way that cancelled itself out. The spin parameter came back at 0.101, below every single measurement ever made for a galaxy at redshift greater than 2, consistent with the slow rotating ellipticals of the nearby universe, the giant dead systems that took 10 billion years to reach this state. I find it worth pausing on what Forrest and his colleagues were looking at in that moment. They were seeing light that had been travelling for 12.05 billion years. Light that left a galaxy when the cosmos was 1. 8 billion years old, and our own solar system would not form for another 7.9 billion years. And that ancient light was telling them, with a statistical precision of nearly 6 sigma, that the galaxy it came from had already accomplished something that our current understanding of the universe said should require the better part of cosmic history to achieve. Forrest's response, in the subsequent press release, was calibrated with the understated precision of a working scientist. This was surprising and very interesting, which is, in the dialect of academic physics, the equivalent of saying the floor just disappeared from under your feet. This is the moment I keep returning to when I think about this discovery. Not the paper, not the press release, not the orbital mechanics of the IFU, or the mathematics of the spin parameter formula. Just that moment, a research scientist in Davis, California, looking at a velocity map from a galaxy that stopped spinning before the Earth existed, and sitting with the fact that everything the models predicted had simply not happened. The data was not broken, the analysis was not wrong, the galaxy was genuinely, inexplicably still. The team's first response to anomaly was, appropriately, methodological rigour. Every alternative explanation, face-on orientation, data artifacts, contaminating sources, was tested and eliminated one by one. The inclination analysis ruled out the face-on scenario. The Monte Carlo redshift determination, with multiple stellar population libraries, confirmed the systemic velocity was accurately constrained. The Voronoi binning scheme was validated against multiple signal-to-noise threshold choices. The spin parameter calculation was corrected for point spread function smearing using published calibrations. At every turn, the data held, and then the morphological analysis added its final piece. The Cersic modelling of the NEACAM images found a Cersic index of N 3.97, essentially 4, which is the canonical value for an elliptical galaxy, as opposed to the value of 1 expected for a thin exponential disk. Combined with the low ellipticity, the galaxy is almost round, with an observed axis ratio of 0.89, and the presence of the low surface brightness asymmetric feature to the northeast. The picture that emerged was of a galaxy that looked, structurally, exactly like a massive elliptical in the nearby universe, not like a young disk-forming system caught early in its evolution. like something that had already arrived at its final morphological state, billions of years ahead of schedule. The paper landed in Nature Astronomy in May 2026, published on the 4th of that month. The title was precise and technically accurate, and told almost nothing to anyone not already working in the field, a massive and evolved, slow-rotating galaxy in the early universe. And in that quiet, methodical title was a revolution in what we thought we knew about the childhood of galaxies, a question that Forrest and his team left deliberately open, because the data demanded honesty was also the question that mattered most. This was one galaxy. Was it a fluke, a cosmic accident, the rarest of rarities that simulations already marginally permitted? Or was it the first confirmed member of a population of objects that our models had predicted would not exist? A population whose existence would force us to rethink not just galaxy formation, but the fundamental cosmological framework within which all of our models operate. That question did not have an answer when the paper was published. It still does not today, and it leads us directly to the deepest stakes of this story. To understand what XMM VID-1 2075 threatens, you have to understand what the standard model of cosmology has built, because it has built something genuinely remarkable, a framework of such predictive power and empirical breadth that it is not an overstatement to call it one of the greatest intellectual achievements in the history of science. The lambda CDM model, lambda for the cosmological constant representing dark energy, CDM for cold dark matter, describes the entire history of the universe from a fraction of a second after the Big Bang to the present day. It tells us how the cosmic microwave background formed, how matter clumped under gravity to produce the cosmic web, how that web assembled into the filaments and sheets and voids that define the large-scale structure of the universe, and how galaxies formed and evolved within the dark matter halos that provided their gravitational scaffolding. It has been tested against the distribution of galaxies across billions of light-years of space, against the temperature fluctuations in the cosmic microwave background measured to 1 part in 100,000, against the abundance of light elements forged in the first 3 minutes of cosmic history, and against the expansion rate of the universe measured through supernovae, Cepheid variables, and gravitational lensing. At every scale, in every direction, across every available observational probe, lambda CDM has delivered predictions accurate enough to make it the unchallenged foundation of modern cosmology. And yet, in the first 2 years of JWST science operations, the telescope having reached its final orbit around the Sun-Earth L2 point in January 2022 and begun delivering scientific observations that summer, something has been accumulating in the data that the model did not anticipate. JWST has found galaxies, extraordinarily massive galaxies in the extraordinarily early universe that the lambda CDM framework did not predict would be there. Not just XMM VID-1 2075, an entire population of objects at redshifts between 6 and 12, some of them appearing only 400 to 600 million years after the Big Bang, with stellar masses that strain the model's timescales for star formation and hierarchical assembly. In July 2022, the first release of JWST deep field images already contained galaxy candidates whose photometric redshifts and inferred masses seemed improbable by lambda CDM standards. By 2023 and 2024, spectroscopic confirmation had proven that several of these candidates were genuine, real, massive, fully formed galaxies in the first billion years of cosmic time, each one adding pressure to a framework that had previously had no reason to feel any. The broader community responded to this tension with the careful language of science. Caution, calls for more data, proposals for modified mechanisms within the existing framework. Perhaps star formation in the early universe was more efficient than models assumed. Perhaps the initial mass function, the distribution of stellar masses formed in each star-forming event, was different in the early universe, biased toward massive stars that converted gas to stellar mass more rapidly. Perhaps feedback mechanisms were weaker in early galaxies, allowing gas to collapse into stars before being expelled by the energy of supernovae and active galactic nuclei. All of these are plausible adjustments to the details of galaxy formation physics that leave the overall lambda CDM skeleton intact. And for much of the tension observed in the JWST data through 2023 and 2024, these adjustments seemed sufficient. The model could absorb the anomalies with modifications to its subgrid physics, the fine-grained, small-scale processes that simulations approximate rather than resolve from first principles. XMM VD1 275 is different. It is not primarily a problem of stellar mass assembly, although it has that too. It is a problem of kinematic evolution, of the internal dynamics of a galaxy, of how angular momentum is acquired and lost, of the physical processes that transform a rotating young system into a dispersion-supported old one. And this is precisely the domain where our simulations make their most confident predictions, because the physics of angular momentum conservation is not an approximation. It is exact. It is not a subgrid parameter that can be tuned. It is a conservation law. The simulations that explicitly address the question of slow-rotating galaxies in the early universe are divided. The Magneticum suite, one of the most detailed cosmological hydrodynamic simulations available, does predict a small number of slow-rotating quiescent galaxies at Z 3.4 formed through the isotropic gas infall mechanism described earlier, but it characterizes them as extremely rare. The Illustris TNG simulation, another state-of-the-art cosmological simulation, predicts that slow rotators should be essentially absent at redshifts above 2. Neither simulation was tested against observational data at this redshift before JWST made such data possible, because no instrument had ever been capable of producing it. This is what JWST has done to cosmology in its first 4 years of operation. It has not overturned the framework, but it has opened a gap, a widening space between what our most sophisticated simulations predict and what the universe has chosen to reveal when examined with sufficient precision. XMM VD1 2075 is the most dramatic instance of that gap yet identified, because it does not reside in the uncertain territory of photometric estimates and mass-to-light ratio assumptions. It lives in the realm of spectroscopically confirmed velocity measurements, calibrated spin parameters, and peer-reviewed morphological analysis. It is not an anomaly that more data will dissolve. It is a fact that more data must explain, and the stakes of that explanation are considerable, because if slow-rotating massive galaxies exist in the early universe at a rate even marginally higher than current simulations predict, if XMM VD1 2075 is not a unique cosmic accident, but the visible member of a larger population, then the formation histories of the most massive structures in the universe need to be rethought. The relationship between dark matter halo structure and angular momentum acquisition, the timescales for major merger rates in the early universe, the efficiency of quenching mechanisms and their connection to kinematic transformation, the very architecture of how galaxies build themselves from gas and gravity. All of these threads connect back to the question of how common objects like XMM VID1 2075 really are. There is something else buried here, which I find genuinely unsettling in the best possible way. Our current picture of galaxy evolution tells a story with a particular direction of time. Young galaxies spin, old galaxies slow. The transformation from one state to the other is a process that takes cosmological ages, billions of years of mergers and dynamical friction and kinematic relaxation. We use this directional transformation as a tool. We read the kinematic state of a galaxy as a kind of clock, telling us where it sits in its evolutionary history. A slow rotator is an old galaxy. That relationship is fundamental to how we date and categorize the objects we see. XMM VID1 2075 is a slow rotator that is 1.8 billion years old. If slow rotation does not require billions of years to achieve, if the early universe contains mechanisms that can produce kinematically mature galaxies in a cosmic instant, then our evolutionary clock is wrong. Not broken, wrong. Telling us a misleading story about the age and history of the objects it claims to read. That is not a small problem. That is a recalibration of one of our most fundamental observational tools. The paper Forrest and his team published in Nature Astronomy in May 2026 was careful, methodical and deliberately open-ended about the formation mechanism for XMM VID-1 2075. This was not a failure of nerve or a reluctance to commit. It was the correct scientific posture in the face of data that genuinely supports multiple hypotheses and has insufficient discriminating power to choose between them. 3 distinct pathways to kinematic stillness remain viable. Each one has internal logic, each one has a problem, and the problem with each one is different enough in character that understanding them together tells us more about the early universe than any single answer could. The first pathway is the counter-rotating major merger. 2 massive galaxies, each containing tens to hundreds of billions of solar masses of stars and gas, approach each other with approximately opposite rotational senses. They collide. Their angular momenta partially cancel. The resulting remnant is dispersion-dominated from the moment the merger completes, inheriting the combined stellar mass of both progenitors, but a small fraction of their original net rotation. Star formation surges in the gaseous starburst triggered by the merger, rapidly building additional stellar mass. An active galactic nucleus, a supermassive black hole accreting gas at extreme rates, ignites in the galactic center, and the energy it releases drives gas outward in powerful winds, shutting off further star formation on a timescale of tens to hundreds of millions of years. The kinematic relaxation of the merger remnant completes within a few 100 million years. The result: a massive, quiescent, dispersion-dominated galaxy. This pathway is appealing because it is mechanistically complete. Every step is observed in the nearby universe or supported by high-resolution simulations. Mergers do produce dispersion-dominated remnants. Starbursts do trigger AGN feedback. AGN feedback does quench star formation. The morphological evidence, the low surface brightness feature to the northeast of XMM VD1 2075, the residuals in the NERCAM-SERSIC modelling, the high SERSIC index of N 3.97, consistent with an elliptical morphology, all support the idea that a major merger has recently occurred in this system. The problem is the timeline. In the standard lambda CDM model, the merger rate of massive galaxies scales with the density of massive halos and their relative velocities. At redshift 3 to 4, the universe was denser and halos were closer together, which increases the probability of mergers. But the probability of a counter-rotating major merger, one with the specific geometry needed to cancel angular momentum rather than amplify it, is a geometrically restricted subset of all major mergers, and the total sequence of events. 2 massive galaxies form independently, accumulate hundreds of billions of solar masses each, approach and collide, complete the merger, undergo a starburst, quench, and kinematically relax, must compress into a timeframe of at most 1.5 billion years. That is a very tight schedule, even acknowledging that early universe timescales for star formation and feedback are shorter than in the present day because the gas densities were higher. The second pathway, isotropic gas infall, resolves the timing problem but creates a different one. If the galaxy never acquired net angular momentum in the first place because the gas from which it formed fell in without a preferred rotational direction, then there is no need to remove angular momentum through mergers. The system was born still, or nearly so. The Magneticum simulation does produce objects like this at Z3.4, and it predicts that the subsequent quenching of star formation in these objects occurs through AGN feedback triggered by the absence of rotational support. Gas that cannot form a coherent disk falls directly toward the centre of the galaxy's potential well, feeding the central black hole at extraordinary rates and triggering the high-energy feedback that drives out the remaining gas. This is elegant, and it has the virtue of connecting the kinematic state of the galaxy directly to its quenching history, explaining both properties through a single physical mechanism, but it sits in tension with the morphological evidence. The low surface brightness feature to the northeast of XMM VID1 2275 is not easily explained by isotropic infall. that mechanism does not predict an asymmetric companion. If the feature is real and associated with the galaxy, it argues for merger activity rather than a quiet, spherically symmetric formation history. The team did not rule out the possibility that the feature is a chance projection, but the odds of a random background object sitting at precisely that position and flux level are not negligible, but neither are they reassuring. If further observations confirm the morphological asymmetry and demonstrate that the companion is physically associated with XMM Vid1 2075 through common kinematics, the isotropic infall scenario is significantly weakened. The third pathway, cumulative minor mergers, presents the deepest timing problem of all. In this model, XMM Vid1 2075 began its life as a rapidly rotating disk galaxy and had its angular momentum eroded gradually through a series of smaller mergers, each one transferring some energy to the system's randoms on stellar orbits, while depositing stars in its outer envelope. Over many billions of years in the local universe, this process demonstrably produces slow-rotating ellipticals with the extended low surface brightness outer envelopes that are a hallmark of accumulated minor merger debris. Many billions of years is exactly what XMM Vid1 2075 did not have. In the first 1.8 billion years of cosmic time, the density of galaxies was high, but the absolute number of massive galaxies available to act as merger partners was low. Whether enough minor mergers could have occurred at sufficient mass ratios to remove the necessary angular momentum within this time frame is questionable at best, and the current size of XMM Vid1 2075, with an effective radius of only 2 kiloparsecs, argues against it because minor mergers are expected to systematically grow the outer envelope of the accreting galaxy, producing systems substantially larger than what is observed. This is the three-pathway paradox. Every mechanism that can produce a slow rotator carries with it a constraint that the evidence for XMM Vid1 2075 either meets uneasily or fails to meet at all. The major merger explains the kinematics and morphology, but strains the timeline. The isotropic infall explains the kinematics and timeline, but sits uneasily with the morphology. The minor merger scenario explains the morphology, but struggles with both the timeline and the size. The data, as it stands, is not sufficient to choose between them, and it may be that the truth is a combination of elements from more than one pathway, a formation history that is genuinely more complex than any single theoretical channel predicts. What the discovery has done is expose the limits of our simulations with a precision that no previous observation could match. Before JWST, it was simply not possible to measure spatially resolved stellar kinematics for quiescent galaxies at Z3. The observational horizon was opaque to this kind of inquiry. Every theoretical prediction about the kinematic properties of early massive galaxies was made in a vacuum, untestable, unfalsifiable, academic. XMM Vid1 2075 has brought that vacuum to an end. For the first time, we have a data point that can be compared against the predictions of the most sophisticated cosmological simulations in the world, and that data point sits in a region of kinematic parameter space that at least one major simulation family, Illustris TNG, predicted would be essentially empty. That is not a criticism of the simulations, it is a testament to what JWST has made possible. The models that have been running for decades, building galaxy populations from first principles in digital universes, governed by the same physics as our own, now have real data to test themselves against at the frontier of cosmic time. Some of them will survive the encounter with their predictions intact. Others will need to be revised. The specific details of how angular momentum is acquired and lost in the early universe, the balance between tidal torques from the cosmic web, the geometry of gas infall along cosmic filaments, the role of AGN feedback in kinematic transformation, the prevalence of counter-rotating merger configurations. All of these processes will need to be calibrated against an expanding observational dataset that did not exist before August 2nd, 2024. There is also a detail in the spectrum of XMM Vid1 2075 that deserves attention, because it hints at a possible role for the galaxy's central black hole that the current analysis cannot fully constrain. The emission line spectrum of the galaxy, the very weak emission sitting above the stellar continuum, shows the presence of ionized neon at 3,869 angstroms and ionized nitrogen at 584 angstroms relative to hydrogen alpha at 6,563 angstroms, a line ratio that is suggestive of an active galactic nucleus rather than star formation as the ionization source. But the complete absence of doubly ionized oxygen at 5,007 angstroms, typically the strongest emission line in AGN spectra, is unusual and not fully explained. The authors note that this is not unheard of in AGN spectra with particular gas geometries or dust configurations, but it adds another thread of ambiguity to the picture. If the AGN in XMM VD1 2075 is still marginally active at the epoch of observation, still in the tail end of the feedback cycle that quenched the galaxy's star formation, then the energy it injects into the surrounding gas might be playing a role in the kinematic state of the system that the current data cannot disentangle from the merger and infall scenarios. What we are left with, in the end, is a galaxy whose kinematic state we can measure precisely, whose formation mechanism we cannot yet determine, and whose existence forces us to ask questions that our models were not built to answer with the precision the data now demands. That is exactly where science needs to be. The next step is not interpretation, it is repetition, not of the same observation, but of the same question, asked of a larger sample, which brings us to what happens next. One galaxy does not a revolution make. Science is, at its heart, a statistical enterprise. A single anomalous measurement can always be dismissed, incorrectly but defensibly, as an outlier, a freak, a cosmic accident that tells us more about the variance of nature than about its fundamental tendencies. To transform XMM VD1 2075 from an anomaly into a result that demands model revision, what the field now needs is a sample, not one spinless galaxy in the early universe, many of them, or the credible measurement that they do not exist, and this one truly is unique. Forrest and his colleagues were explicit about this in the Nature Astronomy paper. The MAGAS 3NE survey has been systematically identifying and spectroscopically confirming the most massive galaxies in the early universe for years, and with each successive observational campaign, first with Keck, with JWST the confirmed sample grows. As of the paper's publication, the number of spectroscopically confirmed massive quiescent galaxies at Z3, with measured stellar masses above 10-11 solar masses, was still in the dozens globally, accumulated across multiple surveys and observatories. The subsample with resolved kinematic data was, until the publication of JO 913 precisely 0. It is now 3, 2 fast rotators and 1 slow rotator. The statistical question of what fraction of massive quiescent galaxies at Z 3.5 are slow rotators cannot be answered from a sample of 3. But the fact that the fraction is at least 33%, 1 out of 3, is itself a number that demands attention. The Magneticum simulation predicts that slow rotators should be very rare at this epoch, without specifying a quantitative rate. Illustris TNG predicts they should be essentially absent. A fraction of 1/3, if it holds as the sample grows, would be wildly inconsistent with either prediction. Even a fraction of 1/10, one slow rotator in every 10 massive quiescent galaxies at this redshift, would challenge both simulation frameworks. The path to building this sample is JWST NIRSpec IFU time, applied systematically to the growing catalogue of spectroscopically confirmed massive quiescent galaxies in the early universe. Each target requires hours of observing time. The field is not uniformly distributed across the sky, and the number of confirmed targets at any given redshift is limited by the depth and area of the photometric surveys that feed into the spectroscopic confirmation programs. Building a sample of 20 to 30 objects with resolved kinematics at Z3, enough to place statistical constraints on the slow rotator fraction at a meaningful confidence level, will require multiple observing cycles spanning several years. But the infrastructure to do this now exists. JWST has demonstrated unambiguously that spatially resolved stellar kinematics of compact galaxies at Z3, 5 is achievable at the signal-to-noise ratios needed for kinematic analysis. The NARSpec IFU, with its 0.1 arcsecond spatial sampling and 730 parsec physical scale at the redshift of XMM VID1 2075, can resolve the half-light radius of these compact galaxies into a sufficient number of independent spatial elements for spin parameter measurement. The methodology, Voronoi binning, PPXF spectral fitting, spin parameter calculation with PSF correction, has been validated on this dataset and can be applied consistently to future observations. The path is clear. What is also becoming clear is that the question XMM VID1 2075 raises about kinematic evolution cannot be answered in isolation from the broader program of JWST galaxy science. Every observation of a massive galaxy in the early universe adds a data point to a growing, multi-dimensional picture. The morphological properties of these systems, their Sersic indices, their effective radii, their structural asymmetries, can be measured from NER-CAM imaging. Their stellar populations and star formation histories can be constrained from spectral energy distribution fitting and absorption line analysis. Their AGN activity can be probed through emission line diagnostics. Their environments, whether they sit in overdense protoclusters or relative isolation, can be mapped through photometric and spectroscopic surveys of surrounding galaxies. Each of these dimensions adds information about how these galaxies came to be, and the kinematic dimension that XMM VID1 2075 has now opened is the one that was previously inaccessible. There is a complementary angle of attack from cosmological simulations. The specific prediction that slow-rotating quiescent galaxies at Z3 should be rare or absent was not made in anticipation of JWST data. It was a byproduct of simulations calibrated against lower redshift observations, extrapolated to earlier epochs without empirical constraint. Now that a constraint exists, the simulation teams can look back at their models and ask where and why the kinematic transformation happens. They can identify the specific merger events, gas infall histories, and AGN feedback episodes in their simulated galaxy populations that produce dispersion-dominated systems at Z-3.4, compare the physical conditions in those systems against the observational properties of XMM VID1 2075, and test whether the mechanisms in the simulations are consistent with what JWST has measured. This iterative dialogue between observation and simulation is where galaxy formation physics progresses most rapidly. The deeper implication, the one that will take longer to work through, concerns what slow-rotating massive galaxies in the early universe tell us about the structure of dark matter halos. The angular momentum that galaxies acquire during formation is sourced, in the standard model, from tidal torques imparted by the large-scale matter distribution on collapsing dark matter halos. The rate and efficiency of this angular momentum acquisition depend on the geometry of the cosmic web, the network of filaments, sheets, and voids along which matter flows, and on the spin parameter of the dark matter halo itself. If some massive halos in the early universe systematically acquire less angular momentum than the model predicts, the discrepancy might reflect something about the geometry of cosmic web filaments at early times, or about the relationship between baryonic angular momentum and dark matter halo spin that the simulations currently approximate. This is a thread that connects the specific anomaly of XMM VID1-2075 to the broader question of whether lambda CDM correctly captures the angular momentum distribution of the universe at the epoch when the first galaxies were forming. And then there is the question of what XMM VID1 2075 will become. In the local universe, the descendants of early massive quiescent galaxies are believed to be the brightest cluster galaxies, the enormous, dispersion-dominated ellipticals that sit at the gravitational centres of galaxy clusters, surrounded by thousands of smaller galaxies and tens of trillions of solar masses of hot, X-ray emitting gas. These objects are the final evolutionary stage of the hierarchical assembly process, the endpoints toward which merging and accretion eventually lead every sufficiently massive galaxy. XMM VID1 2075, already 330 billion solar masses in stars, already dispersion-dominated, already kinematically relaxed, is a plausible early universe ancestor of exactly these objects. If it continues to accrete through minor mergers, as the evidence of the Northeast Companion suggests it may already be beginning to do, its effective radius will grow, its outer envelope will build up, and over the next 12 billion years it will transform from the compact, slow-rotating relic it is today into something far larger and far more familiar. A giant elliptical at the heart of a galaxy cluster, its origin story encrypted in the orbits of 100 billion stars. The universe has a way of making its most extraordinary events look, from sufficient distance, like the most ordinary things. But the extraordinary is there, written in the kinematics, waiting for the instruments precise enough to read it. Every galaxy we have ever seen until this one obeyed a rule so fundamental that we barely thought of it as a rule. Things spin, gas falls inward, angular momentum accumulates, the disk forms, the stars ignite, the arms spiral outward, and the galaxy rotates slowly, grandly, over hundreds of millions of years, sweeping its stars through vast arcs of light against the darkness. That is the story of galaxy formation. That is the story of our own origin. The cloud of gas that became the sun was spinning when it collapsed. The disk of debris that became the Earth was spinning. The Milky Way is spinning right now, at a speed that carries our solar system around its centre once every 225 million years. Everything we came from, everything we are embedded in, everything we can point to in the sky, all of it turns, and then 12 billion light years away, and 12 billion years into the past, there is a galaxy that does not. I have been sitting with that fact for longer than is probably healthy, and what strikes me most is not the physics of how it got that way. The competing merger scenarios and infall geometries and AGN feedback cycles, all of which are absorbing and unresolved, and will occupy theorists for years. What strikes me is what the stillness means about the nature of the universe's variety. We built our models on what we could see, and what we could see suggested rules. Angular momentum is conserved. Galaxies rotate. Young galaxies rotate fastest. The transformation to stillness takes time. Those rules are not wrong. They are deeply, powerfully right. For the overwhelming majority of galaxies across the overwhelming majority of cosmic time. But the universe, it turns out, does not feel constrained by majority. In the vastness of 13.8 billion years and hundreds of billions of galaxies, it has found room to do something that the rules said it could not do quickly, and it did it quietly, 12 billion light years away, leaving a faint smear of light off to one side as its only apparent confession. That is the kind of universe we live in. One that builds frameworks and then, in the corner of the data that we only recently gained the instruments to examine, quietly breaks them. Not to embarrass us. Not because our physics is wrong, but because the universe contains more paths than we have yet mapped, more mechanisms than we have yet named, more ways to arrange gravity and gas and time than our simulations have yet exhausted. Ben Forrest's team will go back. They will point JWST at more massive quiescent galaxies in the early universe and ask each one the same question. Are you spinning? Some will say yes. Most, perhaps, will say yes. But somewhere in that growing sample, there may be others that say what XMM Vid1 27.5 said, that stillness is possible in the childhood of the cosmos, that kinematic age and physical age are not the same thing, that the path to a dead, silent, non-rotating galaxy does not require the entire length of cosmic history to walk. Science does not always deliver endings. Sometimes it delivers a door, slightly ajar, with something on the other side that we have not yet fully imagined. XMM Vid1 2075 is such a door. It has taught us that our instruments, when pointed at the right place, can reveal the universe contradicting itself at a distance of 12 billion light years. It has reminded us that a conservation law, rigorously applied, still leaves room for extraordinary outcomes in extraordinary circumstances. It has shown us that the universe's childhood was not as simple as we thought, that even in the first 2 billion years, when the cosmos was dense and hot and furiously building, it could produce something that looked, kinematically, like the oldest and most settled structures we know, Somewhere out there, right now, there may be dozens more of these still galaxies waiting in the early universe for the light-gathering power of a 500-kilogram gold-coated mirror in an orbit 1.5 million kilometers from Earth to find them and ask the question. What we do with the answer depends on whether we have the courage to let the data tell us something our models did not prepare us for. The universe has been spinning for 13.8 billion years. It apparently never asked this galaxy's permission.